if you see your textbook are very important too. There is this habit students have when they go to their textbook. They will start reading all the notes, theory aspects, like, for example, here they write brief velocity is the average velocity electron has when electric field is introduced, importance of, advantages of. You'll be reading all those notes, but guess what? You enter exam, you notice that most of the things you're expected from in the exam is just the calculation aspect. So I just want to quickly summarize a little of that beginning aspect. Then we go to the core mathematical aspect of what we are here for today. So if you come to this DC circuit, I want you to know that everything we'll be doing before now, apart from capacitor, is simply talking about charges at rest, stationary charges. And mind you, that when we're treating charges at rest, charge there is equals to Q equals to NE. And I told you that this thing simply talks about quantization of charge. Is it not true? And I told you that charge quantization is simply the smallest charge that every other charge is an integral multiple of, right? But now that we are talking about DC circuits, it's no longer going to be just Q equals to NE. We're now talking about charge in a wire. So this Q equals to NE will now have something extra to it. So before that, let's start with what the DC circuit is talking about. So we say that direct current circuit is a type of circuit where current flows directly from the source, type of circuits where your genetics tutor just took the whole time. Type of circuit where current flows. I'm not complaining though, but we just adjust to 5 today. The type of circuit flows. You playing that? Where current, where's your circuit? Where current flows through the circuit. Or should I say, let's say the component, let's call it component, flows through the component. If you write component, you say load. And so you can add directly and back to the source. Now, DC circuits, let me just draw something to show you what I mean by that. You can have situations like this. Assuming I have, let's say, a switch. Even assuming I have that our normal capacitor. Assuming I even have maybe a resistor. There is no use for all these things, so but I'm just trying to show you. Then when I have, let's say this is bulb. Now, all these things that I added here is just to tell you like things that make up circuits. If I just choose to not do this and I just come and say I have this thing directly like this, nothing like this to show you, and nothing of resistor here, just like this. This thing you see here is a component load. We call component anything that has to do with load. This is battery. So battery is a proper example of DC circuits. Now, the bigger parts positive, smaller parts negative. What we are saying is that DC circuit is simply the type where current, we call this current conventional current, because in this part of physics you now come to know the truths. We call this conventional current. Conventional current, convention simply means something you are used to, a way of doing something that has been considered normal. Even if it's not really proper, you just say, since others are doing it, let's do the same convention. So we say that current flows like this, it moves and goes back. Remember when we started that stationary charge, and goes back to the source. So as it's going through this wire, because of the fact that there are charges here, anything you put along it will conduct electricity. So that is DC circuit for you. We have another type which we call alternating. We will come to that. But just know that the difference between DC and AC will definitely come there. But the difference is simply that as this one is moving directly, DC is more like if it moves from this source, instead of continuing directly, it does as if it flows back, go again, does as if it flows back, go again, does as if it flows back. So it's more or less to and fro, till it gets to do what it's meant to do. So years back, there was a war of AC and DC current. We'll get to all those things because we don't have time today. So I'll have time to tell you a lot of stories because this course is deep, really deep, very, very deep. And if we miss the foundation, there will be a problem. So with that said, you now know what DC circuit talks about, moving directly and all that. Now, I want to quickly talk about, before I mention the types and all those things in your textbook, that will be later when I start comparing it with alternating current and the rest, telling you stories about circuits in series, in parallel, and when you are connecting it parallel and series. So please, let's just move straight to the principles. So DC circuit principles, there are three major principles. If you notice, your textbook is writing everything there like notes. And I believe that's not just how we should be because you're going to be solving calculations on all those things. So, principles, DC circuits, principles. So please, we must solve calculations today. That's why we need to parley with me. So this is circuit principles. The first one is the one you are used to, which we call the Ohm's law. That your Ohm's law. You are used to it. And I will be stating the three principles proper with examples so you understand it properly. Then we move into the basic thing we have for today. So the first one is Ohm's law. This is the one I will be treating today. Everything I will be doing today will revolve around this. So I will leave this, I will explain this now. But these two, which we call the Kirchhoff's law. Kirchhoff's law. Another name for this, Kirchhoff's circuit law. Another name for it is KCL. And you have KVL as well. So under this Kirchhoff's law, he gave a rule for circuits, that is when it's current, Kirchhoff's current law, and when it's voltage. He said that the minute you have more than one resistor, one voltage, you are no longer doing just Ohm's law. He said that if you have a circuit, let's say you have a circuit that has more than one voltage, let's say you have more than one voltage plus minus, and you have maybe more than one resistor, his law is saying that the current, let's say this is current A, if you have more than, once it's more than one, like more than one, thereabouts, so on and so forth, automatically, it's not just Ohm's law you are looking at. You're not looking at Kirchhoff's rule and Leibniz's rule. He said that if current is to enter, if current is to flow inside these circuits, that you should look for what we call junction. Another name for junction is node. Now, this junction or node talks about where you have 3 points. The point in the wire where you have 3 points. Let's say this is A. If I notice this point, I'll notice that current can flow here, current can flow here, and current can flow here. Notice that the rest, which we call loop, this point is just having 1 and 2. Is it not true? This one, this point here is having 1 and 2. And this particular point is also having 1, 2, and 3. You see this? So this is a junction, this is a junction. 1, 2. 1, 2. So we can just say that all these other ones are not junctions. So we can simply say that a node is best put this way. When you have just 2 points, you call it node. But when you have 3 points, you call it junction. Can you hear me? Which means that every junction is a node, but not every node is a junction. So in your textbook, they just wrote node there. Know the difference. When you have a point that links 2 wires, or a point where current can pass in 2 directions, you call it a node. But when you have a point that links 3 connections, that links 3 sources that current can pass through, you call it a junction. So every junction is a node, but not every node is a junction. So Kirchhoff's rule is simply about junction. So he's saying that the current that this particular junction will receive, let's say the current is flowing from here now and coming here. He's saying that the current that this thing will receive, I will still teach you this principle proper. I'm just explaining that the current it will receive is equal to what it will give out. This principle is saying that whatever current is coming from here and flowing into this, that is the junction, that point that has way, or maybe like this. Just notice that that point is linking 3 things. That the current it will receive, the current coming inside it is equal to the current it's giving out. So notice that as it's coming here, it's going to be given out this way and going to be given out this way. Have you noted that? So please, this Kirchhoff's current law, the first one, talks about that the current entering a junction is also a node, but not every node is a junction. Note it, that the current entering a junction is equal to the current going out of that junction. Just note it. As for you, maybe understanding the rules, the formulas and everything, you will definitely get it, enough of it. So just write for me. Kirchhoff's current law states that the current entering a junction, you open a bracket, you write a junction is also a node, and not every node is a junction like this. That is his current law. So this law obeys the law of conservation, which states that current cannot be destroyed. That's every charge, that law of conservation of charge, which states that charge does not get destroyed, but rather can be transferred from one point to the other. I taught you conservation. So if you've noted this current law, the next one is voltage law. It's still under this Kirchhoff's rule. So I said Kirchhoff's rule gives 2 accounts. One is the Kirchhoff's current rule, which we call KCL. Second is KVL. I don't have time, so don't come and be making me repeat myself. I said that the current rule says that every current entering a junction is equal to the current going out of that junction. That is the first rule. The second rule is that the sum, that is the voltage ohm. I want to put it. He says that the sum of voltage in a circuit, will always be equals to 0. The total voltage in a circuit will always be 0. Just note that. So if you've noted that, I want to play. Remember, this is the introduction of this class. So that's for Kirchhoff's rule. Now, for number 3, which is Thevenin's rule. His rule simply, that is Thevenin's law. His rule simply says that for a linear circuit with, please be fast, for a linear circuit with 2 or more resistors, voltage, that a circuit can be created for the resistor and voltage with just Thevenin's resistance and voltage. I said for a linear circuit with 2 or more resistance. Use resistance because the work of resistor there is to give resistance. For a linear circuit with 2 or more resistance, voltage. For a linear circuit with 2 or more resistance, voltage, a circuit can be created for it. A circuit can be created for it that sums up the total resistance. A circuit can be created for it that sums up the total resistance and the total voltage, known as Thevenin's circuit. Known as Thevenin's circuit. So if we have as many resistance as possible in a circuit, as many voltage as possible in a circuit, then we can just round it up to just 1 and 1, so that we call that Thevenin's circuit. This is the spelling of Thevenin circuit. So please, these 3 principles, notice that what we are going to be doing as we progress. Why I gave you that is so that as you are reading and making your research before we get there, you can just have it in mind that this is the type of thing I talked about. Then, once we are done with all the things we are doing today, as we progress, we are definitely getting there to circuit classes. Now, please, before I start Ohm's law and any of these principles or going deep, I want to first start with the basics, because you cannot talk about electric current without talking about charge. And I said that when it concerns charge with a source, the minute a source is introduced, example battery, the minute a source is introduced, example battery. Remember when I was teaching you capacitor, it's part of this thing, it stores charge. From the part where I got to capacitor, that's where I started teaching you outside stationary charge. Can you hear me? So have it in mind. So the minute you introduce a source battery, Q is now going to be equals to NE. Then have A and the L. That is area of the wire and length of the wire. It's no longer going to be just when it was stationary charge or electrostatics. For electrostatics, we use quantization, where we said that it is the smallest charge, that every other charge is integral multiple of or are integral multiples of. So, but when it has to do with charge in a wire, it's not going to be that our normal NE, then times area of that wire and the length of that wire. Just note this is constant. For the whole of this session, the whole of everything we are going to be doing under electricity, have it in mind that it's not just going to be Q equals NE, but Q equals NE and area of the wire and length of the wire. Now you need to remember that once upon a time in first semester we did that velocity is equal to displacement over time. Do you still remember? Yes. But now, since we are talking about wire, what that wire has is L length, and displacement is the same thing as length, share you know. Yes. So I will now have over T, V equals to, now child of God, if I make L the subject of the formula here, I will have V T, shall we? Yes. Equals to L. You agree? Yes. Okay. Now that you have V T equals to L, I want you to check something for me before I come to that. Shall you know that A is meter squared and this is meter? Do you agree? Yes. And this is meter cubed now. Yes. So if at any point, I come to any point where I say divide both sides by AL, divide both sides by AL, NE is equals to Q over AL. I will not be wrong. And this thing is volume. Sure you know that this thing is volume. Yes. So this is charge. So another way to put it is that NE can also be seen as charge density. Charge density. NE can also be seen as charge density. Have you written it? There now, but before I get to all those Ohm's law and all those things, if you notice, most of these things I'm teaching you, you will just come and see formula one place in your textbook, but you will not know like the roots, the source, how it came about. So that is what we want to do here, so that before we rush into Ohm's law, if we rush into Ohm's law without you getting this thing, you'll be confused. If you question, you can never be guess wrong. So you've noted that charge density. Now, if I've noted that, just write it for me. If I've noted that, I will still come back. Before, let me leave this small. Come. Do you remember that F is equals to QE? One time we did F equals to QE. Do you still remember? And we now say that MA is equals to QE. Do you remember? Where we now said that if you make a certain formula, divide both sides by M1, is it not true? Then this will cancel this, that A is equals to QE over M. You still remember this thing? Then we also did that the velocity motion of charge now, that velocity is equals to U plus AT. That then when this one is 0, V is just equals to AT. Shall you remember? Then that V is equals to QE over M times T. Do you still remember this thing? Then that V is equals to, let me carry this T and come here. This will be something as saying Q over M times T. Then times E. Do you agree? Sure is the same thing. If from here, this thing that you see here, this thing, the whole setup you have here is represented under direct electricity, under electricity as mu like this. We call this thing electron mobility. Then bring this E here like this. This thing you are seeing is this thing. So a situation whereby they gave me this thing, that means that what this thing means is that V and A bar for electricity, V and A bar is also called drift velocity. I will explain drift velocity. But just have it in mind that the velocity of a charge or current once there is source is not just called velocity but drift velocity. I'll still tell you why it's called drift velocity. So the velocity you have whenever there is battery or a source charge moving a charge to cause current, the velocity there is not called velocity but drift velocity. So if I know that anytime I'm to calculate drift velocity and I'm giving charge, giving mass, giving time and electric field, I can just use this. But anytime I am told that there is something like electron mobility given, I can just replace it with this and then this. So I said that everything you see here is what you call electron mobility. Note it, it's very important. Why this one is VD, drift velocity. I'll still tell you what drift velocity is all about and why we call it drift instead of just velocity. But have it in mind that the velocity you have when you have a source or a battery or anything moving current, causing current, is called drift velocity, not just velocity. So you've noted this one. Now that you've noted this one, have it in mind one side because I'll be making use of it somewhere. I want to claim this and this because you've noted it. I want to claim this and this so that we can go back to using charge. You've noted it. Now see something for me. If that is the case, that means that if we said that in movement of charges to get electric current, that there's something like velocity, that is drift velocity. This is also drift velocity. This is also drift velocity. Remember that this velocity, from the velocity we use the equation of motion, is still the same thing. Now, if that is the case, let's now come here and replace this L with this thing. So that you now see that this will now be VDT. Then AEN equals to Q. So if you are given drift velocity or velocity and area and time and charge, the smallest charge, which is electron number, then and you are giving this, and I'll still tell you what this n is. You can use this formula or you can use this. So please, whenever velocity, you are talking about velocity, drift velocity on its own, this is your formula. Whenever you are talking about drift velocity in relationship with electric field, this is your formula. And whenever you are talking about drift velocity in relationship to electric current, we are going to get that one. Drift velocity in terms of what it is, this is your formula. Then, drift velocity relationship with electric field, this is your formula. Drift velocity relationship with electric current, that is what we are going to get very soon. So if you've noted that, let's continue. So if I know this, I will now tell myself, what is a current? We know that charge, from the beginning, we say that it is the internal property of the system of matter or material that makes it attractive or repulsive, charge. But this charge, once you are talking about charge movement and you are comparing it how it happened in time, is now current. So we say that the charge you have in a cross-sectional area, the charge you have in a given area with time or by unit time is known as current. So I like to tell my students to see charge the same thing as current. Just that current now talks about that charge you have within what time is it. So we said that current is charge in a given surface by unit time. So equals to Q over T. Current charge per unit time. So it's the same thing, they are directly proportional. So if I have this, it simply means that I will be equals to, notice something. Do you notice that Q, everything Q here can be the same thing as saying N-E-A-L all over C. Share you agree? That is, if I'm using this first one, if I'm using the first one, but in a situation where I'm using the second one, this can be the same thing as saying N-E-A-V. This B, write it small so you know that it's not like B separate. It's just trying to tell you that velocity you have when there is a battery or something making charge to flow is the velocity. So put the T here, this everything here. So now divided by T, this can cancel this. So that current is the same thing as saying N-E-A-V. Now, current is equals to N, and we know that this N is talking about that N we talked about that time when we did quantization. So, but I will tell you what this N properly means. When there is source charge or there is battery, something that is causing charge to move. If there is nothing causing charge to move, it will be stationary or at rest. That is why we have to do contact or rubbing. Then A, V, B. So please, let's make this V here subject of formula. If I make that V subject of formula, you will see that your genetics tutor just spent the whole time.
You came late.
She came late?
You.
No, I did not come. It's supposed to be 11 to 1 now. She's supposed to start the class. Oh yeah, I will have I, women supporting women. Eh? It's well. So N-E-A-V-D. When I make this solid of formula, you see, we divide both sides by N-E-A. All over N-E-A. This will cancel this. So V, that is D, is equals to I all over N-E-A. Oh, yeah. That means that whenever I am talking about current, whenever they give me current, and I have to find the velocity, this is the formula I need to use. But where you will have issue is this N. So let's talk about this N before I progress. Let's talk about this N. We know that first class when we started, the N, they always tell us to find the number of charge. So this N can mean number of charge. It can mean number of charge. That is when you are finding N. But a situation whereby you have this kind of setup now, this setup, what is the N there? So it simply means number of, not just charge, but free electrons. Free electrons. So the N there is simply saying, if I have, for example, a basin, sorry, maybe this is copper. This N here is saying, if this is copper, for copper to be everything here, an atom of it should have maybe one electron. Then that by the time you have this one electron packed up inside it, they want everything that is here started with just this one now. Is it not true? So what that N is simply talking about, another way to put it is, if you don't see it as number of free electrons, you can see it as charge carrier density. They are telling you how is it packed? How is it packed inside that particular atom? So I'm giving it to you so that when you start seeing questions, you understand what it means, why it is like that. So N is also equals to charge carrier density. Charge carrier density. Listen to that English. The charge carrier that causes density. Density means something being packed. If I've told you this thing, I've explained it before. The depth of something. If you have to compare foam to sand inside the same liter, sand will be heavier. That means it's more dense. So the charge carrier density, you are looking at one of it that makes up that density, the N, that is it. So if they don't call it free electrons, they call it charge carrier density. Another way you need to see this is as number of atoms. Number of atoms. And whenever you are to find this using number of atoms, it simply means they did not give you this. In these two cases, when I explain these two cases is that they might tell you the number of free electrons is 1.6 times 10 raised to the power 29 or something. Just know that they are talking about that and that you use that as NA. Or they tell you the charge carrier density is this. Just know they are talking about that NA. But in a situation where they did not give you, in that case, the only way for you to find it is using your chemistry knowledge of amount of substance, because any stands for amount of substance, mole. Mole talks about number of 18. So if you remember in secondary school, in that case where they did not give you this, you must now use this knowledge of chemistry in secondary school to find your charge carrier density. Whatever you find using this our secondary school knowledge will be the same answer with whatever they give you here. It's constant. So let's go back to secondary school and remember that any can be this. Any can be 5 things. Any can be 5 things. Mole can be 5 things. We normally say mole, any can be equals to mass over molar mass. Any can be volume, but we are not dealing with volume here. I just want you to write it so that in case you see question, you know it. 1, 2. Any can be number of atoms over Avogadro's constant, which is 6.022 times 10 raised to the power 23. N can be equal to concentration, that is molarity. You learn it this semester in chemistry. Molarity and molarity. They will teach you this semester. So concentration times volume. And that is why during your chemistry practical in secondary school, you see CAVA over CBV. So this is the third one. The fourth one. Then NA from BV equals to nRT. NA can be, so NA can be equals to RT all over PV. That is gas constant, temperature, pressure, and volume. So these are the 5 formulas of mole. Now that you know the 5 formulas of mole, whenever you are finding any, okay, wait, sorry, thank you, bless, PV over RT. So whenever you are now finding the NA, it was not given. They did not give you the NA, and you have to find it. What you must make use of is simply these two. This and this. And how do I do that? I don't want to. Okay, I can. What I'm teaching you now is not something you will not see. Once questions are coming, your understanding of this will help us. So first of all, we come to the first one, which is mass over molar mass. So small m for mass over molar mass is equals to, so it's the same thing I said, if this is mole, let me use this thing now and replace this thing that is here. So if this is mole, it's the same thing with any that is here. Carry this and put here to face this thing. So equals to number of atoms, which is N, over this Avogadro's constant is represented with NA like this. So making N subject of the formula, you now have Na equals to mass over molar mass times Na like this. So if, now notice there is nothing like mass of anything. What you have is like that is constant. What you have is this molar mass that is constant. But you have the density of things being constant. Sure, you know. You have the density of things. For example, if I ask you the density of copper, it exists. If I ask you the density of aluminum, it exists. But if I ask you the mass of copper, it's either you be telling me mass of copper in what sample, or are you talking about the molar mass? So for that reason, this mass has to be replaced with density. And how do you do it? You simply tell yourself, if density rho is equals to mass over volume, Let's take it that the volume we are having now is the volume for just one, that is STP, which is 1 meter cube. So that means that if that is the case, this is density equals to mu over 1, which is equals to mass. So considering this to be equals to 1 meter cube, this is over 1. So density now will be equals to mass. So if I know that, whenever you are finding this, because density is always stable, because this mass, you replace it with density all over the molar mass, then the number Avogadro's constant, which is 6.022 times 10 raised to the power 23. So if any was not given, then do not mention any as the first two things I said, the free electrons, charge carrier density, and you have to find n. This is your formula. Always find the density of whatever you are given all over the molar mass of whatever you are given. If it's copper, if it's zinc, then Avogadro's constant is constant. Multiply it. Your ending will give you whatever free electron you are supposed to point there. That is this. So this is the sentence I'm saying. This is the formula for finding number of free electrons, and it's also the formula for finding charge carrier density when it's not given. So with that said, let's go back. I want to play.
No, wait, put it on the last one.
I'll be fast. So if you notice, we now know. Hey. This one is from density formula, and density equals to mass over volume. There are things you are not supposed to be thinking of now that you are in second semester. There are things that should be very free with you. You don't have to be spending your time killing yourself. Density will lead with this one. Why do I have to do this one? And another thing that should not be stressing is how to carry something. Something is equals to an interchange. Alright, be fast. Let's go back. Now that you know that any, for sake of questions, it helps us. Now let's go back to our business. First, our stationary small thing will do Q equals to NE. Now that we are here, small thing now will do Q equals to NEAN. So this is our charge quantization here. We must include the area and the length. So small thing again, I also say that this is equals to NEAVDC. Is the same thing. So small thing again, since I'm talking about electricity, flow of charge. The flow of charge within a time gives you currents. So if that is the case, I can also bring my current. So I can say, using the same principle, it's just NEAVD. Shade? Is it not true? Because by the time you put that in, the T will cancel it. So if I know this, I can now say, there is something we call current density. The goal is to point out everything we need before we now say that we are able to solve questions. Now, current density is simply gotten by saying we cannot have current density to be, first of all, current that you know happens on a surface. Sure you know. And whenever surface is the area of concentration, we are now considering the density there to be over area. Whenever length is the concentration or what we are having as our point of view, that means it will not be over the length as density. So in that case, this current here, the only thing representing surface here is area. So if I bring out that area, 1 over A, it will be equal to NEVD. So everything here is what we call current density. That means that this current density in physics, it is represented with J. You hardly see alphabets that has J in physics or chemistry. So whenever you see it in physics, know that even in your periodic table, you don't have J here. So whenever you see, that's the only alphabet not in the periodic table. Yes. So whenever you see this in physics, you say? Okay, but you're not talking to me. I said this now is J, it means current density. It means current density. So I over A, current over area is current density represented with J. So that J is equals to NEVD. So we've gotten drift velocity, we've gotten what drift velocity, but I've not told you what drift velocity is. We know the mathematical expressions now. We know that it is velocity that is there when we apply source, battery, or whatever, but we've not properly defined it. So now that you know current density, what it is, let's define drift velocity. And I've already shown you the relationship between drift velocity and electric field. You cannot be coming to my second semester tutorial to check if the tutorial is going well. Remember, it's first semester they used to check if tutorial is going well. Second semester is your coursemate you ask, should I join? Or say yes, you join. Or say no, you stay in your house. You don't come here second semester to check if tutorial is going well, because it's going well. Oh yeah, so I've gotten current density. This is my current density. So I can as well say that current density is always going to be equal to NA, then E, and this E, we know this E to be 1.6 times 10 raised to the power minus 19. Don't forget it, drift velocity. So it's the minimum charge, Now please write for me in your book, drift velocity. Write for me in your book, drift velocity. You're playing now. Drift velocity. Just be playing. Okay, we said that. I know, let me first start with how your textbook defines it. The average velocity possessed by a charge when electric field is created. Average velocity possessed by a charge when electric field is created. Now please, for the sake of tutorial, we say that drift velocity is the random motion experienced by electrons. The random motion experienced by electrons. The random motion experienced by electrons in a circuit. The random motion experienced by electrons in a circuit that causes it to drift. Or you say to move slowly. That causes it to move slowly. The random motion experienced by electrons that causes it to move slowly when electric field is created, or you say in an electric field, that causes it to move slowly in an electric field. I think it's better that way. That causes it to move slowly in an electric field. Full stop. Now see what I mean. We know that if this is like our load, we call anything that comes, please pay attention, we call anything that comes in between load. We call anything that comes in between this voltage as is moving load. This is conventional current. Conventional in the sense that in physics we generally believe that since proton and electron, since they are having the same number, that is the same charge, 1.6 times 10 raised to the power minus 19, that even if it's going this way that we are used to, starting from origin and terminating here, then no problem. But in reality, for electricity to be experienced or for electricity to be there, what you actually have is electron flow. Electron is flowing this way. Electron flow. So what it means is that, first of all, electron is lighter than proton. Secondly, you have many negative charge here than on the positive. And we know that in voltage, we say that voltage moves from region of higher potential to lower potential. So it's more like if you check the balance in between this electrode, you know you have the cathode for positive and anode for negative. So if you check the balance, it's more like you are having more negative under your anode than on the cathode that receives negative. Cathode, if you remember, electron is also called cathode ray. So cathode receives negative, so it's positive. So because of that, there's a balance in such a way that the pressure will be on negative moving faster than the positive. So for that reason, the reality is that the flow of electricity is this way. But physicists now say that since we know that, yes, these two have the same number of charge, and conventionally from origin, ab initio, what we normally say is that charge moves this way. So we say let's stick to the conventional current flow using positive to be the movement. But when you're not talking about drift velocity, you now have to think what is proper. In drift velocity, we say that electron is actually moving. It's the electron that is moving. And that movement of the electron is random. In the sense that as you have, for example, let's say I have this to be my wire, because it's inside wire that all these things are happening, inside this wire now. This is area, this is area. That if this is positive and this is negative, that before now, if I have negative charges scattered and positive scattered, that the minute I induce electric field here, that as the positive is moving, that the negative will flow faster, and that movement will make the direction to be in such a way that I have this, I have this, I have this, I have this. But because it's random, some of the negative charges, these are negative charges. Some of the negative charges will also tend to be moved by this positive. As this is coming in, some of the negative charges will also tend to be in this direction. And the ones that are in this direction, that are going straight, they will be hitting each other, they will be colliding. There will be collision of negative charges. That collision of negative charges is what causes drift velocity. So it slows it down, unlike the positive charge that will move without any collision. Positive charge is heavy, no collision. It will just be moving on its own. While the negative charges that are in excess, that are supposed to be moving, will be colliding with each other. So as they collide, there will be drop in the movement. That drop in the movement, of negative charges, I'm coming, is what you call drift velocity. So there is motion. The motion is supposed to be that electron is flowing as fast as possible. But because there are too many electrons, there will be collision between them. So it brings about random movement, and that random movement makes the velocity to drop. So we say that drift velocity is always slow, it's not fast. So it is slow. So whenever we are talking about drift velocity, it simply means that the movement of drift, of anything drift, is from the negative to the positive. You can see it in objective question. How is the movement of drift? In what direction? It's always from negative to the positive. And that negative is in excess. And because it's in excess, there will be collision. That means there's random movement. And that random movement causes it to slow down. So it's not very fast. So that is why we say that it is drift velocity. It is not as fast as possible. Somebody called me. I had some. Okay, please. So you've noted that. And I believe this is the reason why physicists now said, conventionally, we know that electron is what brings about electricity. But since there is drift in the movement of electrons, it simply means that current will go much faster than this one. That is, current will go much faster when you think of it from the positive than this one that collides. So that is why we stick to the conventional use of current being from positive to the negative, instead of from negative to positive, which is actually electron flow, because it's negative charges that cause electricity. That's the point I'm trying to make. But because of that, we are not saying that we should think of it in that manner that electrons are much, they are random, they collide, they bring about drifts, slowing, rest in their time. So we say that current will move faster on these axes. That is what we're sticking to the conventional current. So if you've not noted that, that is all about drift velocity. The next thing I want to talk about at this junction, but before I progress, ask your question. Any confusion, ask your question before I progress. We understand. Because I don't have my answer.
I can say that negative will always be in essence.
Yes. And what I'm trying to say is that there will be more of the negative than the positive. If you check, that is why you also need to go and check your battery. That is, if you check your battery, the composition, the inside. If you notice, you will see that anytime in chemistry that you have equal positive and negative, you say that there is neutrality. But the minute you have more positive, you say that it's an ion, a positively charged ion. And the minute you have more negative, you say it's a negatively charged ion. Shebi? Now you will notice that if you check whatever you're doing, those your oxidation reaction and whatever, what is happening inside that battery, you will see that it is always more of the electrons moving. That means that there is excess of that electron than the positive. And that is why you say there is an ion inside. Such that if you use a battery that has, let's say, 1.5 voltage on something that requires maybe 220 voltage, electron will actually move, but it will not power that thing. What it will just do is that it will make the electron there to just dissipate and not bring about current. We'll still get to that. So what I'm saying in essence is that there will always be creation of ions for electricity to be created. One must be more than the other one. If they are neutral, equal, if there is balance, it can flow. So one must be more. The one that is lighter must be more. If it's not more, there will be no flow. It will just sit there. In fact, look at it this way. We know that what this thing has is voltage. Look at voltage as something that is like a pipe. If you pour water here, and this thing is sitting comfortably, maybe small water here, it will not move. Small water. But the minute you come and carry this thing up small, upon this small water, the minute you carry it up, you notice that water will flow. Is it not true? So see voltage as pressure. See it like a pressure. That the minute one tends to be higher than the other one, there will be flow. But the minute they tend to be equal, there will be no flow. So it has returned back to its original state, which is zero. So think of it that way. I believe as you make more research in the composition of battery, it will be clearer, and that is not what I'm doing today. I'm not trying to be going into oxidation reaction to start telling you zinc one side, what's it called, steel on the other side, trying to do all those electrons and balancing. No, that's not what we're here for. So please.
Sir,
Okay.
you said that there will be pollution of negative charges, like inside that's this one.
You're talking, I can hear you.
And regarding the pollution of positive and negative.
I never said that your positive will collide.
Okay.
I said that drift velocity is brought about by the collision of electrons. I never said positive charges. I said the negative charges. So don't think in that sense. So drift velocity, the movement, the direction. See, the summary is simply like this. The summary I want you to get from it is that the reason for drift velocity is simply electron flow becoming slow because of the fact that there is collision. And you also need to know that unlike when I taught you insulators, Gauss law, where I said that you can't have conduction, electric field inside a conductor. You still remember? I once said you can't have electric field inside a conductor. But whenever there is a source like a battery, whenever there is source like a battery, whatever that is powering, electric field can be created inside a conductor. So note the difference. Be noting all these things I'm saying now, and thank God for your questions. Whenever there is a source, unlike when there is no source, which is for stationary charges, where we said that you cannot have a electric field, you cannot have an electric field inside the conductor. For any particular system where there is a source that makes charges to flow, electric field can be created inside the conductor as well. And now what I'm talking about is what happens inside that conductor. So inside that conductor, the movement of electrons there is random. And that random movement causes drifts. It causes it to slow down. So that is why we use conventional currents, that the positive is the one that now moves faster. So please note that. Let's move to the next point because we don't have time. Write for me. Write for me. DC current principle 1, Ohm's law. DC current principle 1, Ohm's law. Yes, now I can enter Ohm's law because now you know what charge is. You know what current is. You know what current density is. Yes? So I can enter Ohm's law now. I said DC circuit principle. Or I said DC direct current circuit principle 1, Ohm's law. So you can see in your objective question, they tell you the law that talks about voltage, current, and resistance is what law? Ohm's law. So note that. So this law says that, I know there are ways they state it in your textbook, but I'll first state my own. So you now use your textbook own and answer it can also be stated. So the work done in moving, the work done, and you know that work done is simply voltage, Shebi? Is it not true? So the work done in moving a charge, or you say a unit charge, through a metallic conductor, the work done in moving a unit charge through a metallic conductor, the work done in moving a unit charge through a metallic conductor is directly proportional to the output. Open brackets and write current for me there. The work done in moving a unit charge through a metallic conductor, you can say pass. Okay, yes, let's do so. Is moving it through a metallic conductor. The work done in moving a unit charge through a metallic conductor is directly proportional to the output. You write current for me. So whenever you move charge, whenever charge is flowing, the flow of charge at any given time is what you call current. Can you hear me? So if that is the case, the output or the end product of charge movement is what you call current. So have it in mind. So if that be the case, that is what Ohm's law is talking about. In your textbook, you will see something like current flowing through a metallic conductor is directly proportional to the potential difference and all those things. It's the same thing. But I just want you to know that what Ohm's is just talking about there is simply that whenever you apply voltage, and voltage talks about moving charge, that whenever you apply voltage to move a charge, that whatever output you have is proportional to that work that was applied. That is the voltage that was applied. So that is why you have that this is V directly proportional to I. Now when you introduce proportionality constant, which is equals to, this becomes equals to I R. Note this. And this R you are seeing here, is what we call resistance. We say that this resistance, I said it in the note I posted. They can ask you in an exam, objective question, you might see one formula like that you know. Maybe V directly Q here, directly proportional to C. V. This talks about capacitance, is it not true? Where Q equals to CV. Do you still remember? You might see something like this. They tell you the capacitance of a particular plate or a conducting plate is proportional to what? You come and see the charge, voltage, area, dielectric constants. Then they come and tell you A, I and I. B, I and I. C, I and IV. What's the answer? I will repeat it. Let me repeat it. They will come and tell you the capacitance between a conducting plate is dependent on. They come and write first of all A. Yes, they write A. They write charge. They write B. They put voltage. They write C. They come and put area. They write B. They come and put dielectric. Then you now come. They come and write. Okay, let's say they said I charge. Sorry. Okay, let's say they say I charge. Don't worry. We must get there. Then I voltage. Then I. Then they tell you area. Then IV. Then I come and tell you dielectric constant. That is ER or K. Now you come and see option A. I and I. Option B. There's capacitance is dependent on any of these. Then you come and see option B. I and I. Option C. I and IV. Option D. I and I. What's the correct answer? A. Somebody said A. Who said A? The correct answer. Who said A? The correct answer. You got it, but you got it wrong. So you see, this will confuse you. Very tricky. So please. The correct answer, those of you that said C, you are correct. The correct answer is area and dielectric constant. So, whatever you have, anytime you have a constant, this thing here is a constant. Anytime you have an equation, directly proportional to anything, or inversely proportional to anything, and on introduction of equality sign, you come and introduce a constant. That constant does not depend on them. It only tells you that it increases or decreases, but that constant will always be there. For example, whether in this case now, whether the voltage is changing or decreasing, provided you have a conducting plate, there must be storage of charge. Be it that the storage of charge is reducing or increasing, but the voltage itself changing and the charge changing does not make the capacitance, the charge that is supposed to be stored, disappear. The same thing with when you have a wire. Whether there is voltage there or there is no current, provided that there is existence of heat in any amount, there will be resistance. So even if that thing is conducting, current is flowing or is not flowing, provided that there is a wire there is resistance there. It has the ability to resist any flow that wants to happen there. The same thing with whether there is charge here or voltage here, it has that ability inside, that innate ability to store charge. That is what it means. So once you introduce equality sign, that thing that you introduce is a constant. It does not depend on this. What it just does is that it tells you that there is an increase in this direction or decrease. Note it. So what it means when you hear dependent means, does it really need this thing to exist? Once that C must be there, is the constant there. So have it in mind. I don't know how to put it, but just know it that for the fact that you are introducing something after your equality sign, that thing is a constant. It doesn't depend on the values left and right. The only thing it tells you is that if this one is increasing or this one is decreasing, it will be playing along with regards to if you make it equality sign, what it's showing you. So if I've noted that, you now know Ohm's law, but that is not all. So now that I have this Ohm's law, The essence of this resistance, watch you see. Sure, you know that the major electricity that Nigeria is using, it comes from far places. There's one in Niger State, different places, all those hydro dams and the rest. Now, imagine that you are having to transport electricity without a resistor from far distance. Before you get to your house, the wire will heat up. The wire will heat up. All the electricity is supposed to come to you will heat up, become heat, or even burn, catch fire. That is why you see sometimes something that is connected to electricity to catch fire. Because it is more than the load itself is more than the material of that wire. So that is why we introduce resistors. Resistor makes it in such a way that the energy there that is supposed to heat up the wire is actually converted inside that resistor. Because of the resistance it offers, it makes that heating to happen to the resistor itself. The same way with when they tell you, use fuse before you put your charger, that if that thing wants to burn your charger, it will cut the fuse. And when it cuts that fuse, there will be an open circuit, so your charger will no longer burn. That is the same thing that all this resistor is doing. So that resistance it offers to the flow of current makes it that what is supposed to happen to your wire, I'll still define resistance, but I just want to tell you the reason for resistor that brings about resistance. The heat that is supposed to happen to your wire and whatever it is that is supposed to make your current to be interrupted will simply happen inside the resistor, within the resistor, because of the resistance it's offering. So that is why in Nigeria we say that Nigeria actually operates current at high voltage and low current. So high pushing, he pushes it highly, and by the time it gets to you, the current will be low. And why is it low? Because of the resistance offered. So know that. So if that be the case, let's say I make, why did I say resistance offered? If I make this resistance subject of the formula now over I over R, this cancels this. You see that V over I is equals to R. Is it not true? This is directly proportional to this and inversely proportional to this. So the more the voltage, the more the resistance, the lesser the current. So this only tells you what ratio this one will be increasing and decreasing. Not that it's dependent. That is for every equality or proportionality sign. Note that so that they don't trick you. So now that we know this, let's now define resistance. I can claim. We say that resistance is the opposition offered to the flow of current. We say that resistance is the opposition offered to the flow of current. The opposition offered to the flow of current is known as resistance. The opposition offered to the flow of current is resistance. So you now know that resistance can be given by V over R. Sure, you've noted this one. But as my student, I want you to always not think of this way. Just be thinking of it from this angle. This one will help you more. Because majority of the things you are solving that will involve you doing R equals to V over R for currents. They are simple mathematics. They are the simple parts. And nobody in physics wants to give you much of this. So it's best when you're always looking at it from this angle. But whichever way, you can do calculation. So now, if you know that it's the opposition offered to the flow of current, you will now need to know that this resistance, practically, since we are talking about, if you notice, when I started, I said Q is equals to NE. And instead of NE, I now introduce A and I introduce L. Is it not true? So everything that has to do with whenever there is a source, that is current, electricity, or whatever, this A and L, very important. So I will compare resistance to area and length. So let me compare resistance to area and length, because that's the practical thing, the wire. So the resistance practically, the longer the wire, if the wire is very long, it will take time for your current to travel compared to when your wire is short. If you are closer to me, if I want to react, I will get to you faster. Is it not true? But if you are further away, it will be harder. The same approach. So your resistance is higher when you are far compared to when you are close. So for that reason, we say that resistance is directly proportional to length. The bigger the length, the bigger the resistance. The smaller the length, you see, the resistance will be small. While if you have an area, maybe the wire is too tiny. If the wire is too tiny, you will see that should be smaller wire now, it has smaller surface, is it not true? The resistance will be high. The flow of current will be limited. But if it's too big, too large, you will see that the resistance will be small. Flow will be there. It's just like maybe you are inside this hall now, where I want you to view it. And inside this hall that we have very limited chair. Everybody is seated together, compacted, like two jam-packed. You will see that movement is limited. Is it not true? But if, as we are now, we have so much space for everybody to sit down, there is flow. So that is why we say that once the area is big, resistance is small. And when the area is small, resistance is high. So they vary inversely. So 1 over A. So if I'm putting this together, I will say that this is directly proportional to L over A. The bigger the wire, the thicker the wire. That is why if you are doing management, you are doing, for those of you in future that we have business places, when you want to buy wire, the electrician will be telling you, small time the thing will catch fire, God forbid. So please, this should teach you that if the wire is thicker and bigger, it saves you future accidents. So the bigger the wire, the lesser the resistance, the more current will flow. While the lesser the wire, the tinier the wire, the more resistance you have. So on introduction of what's it called? Equality sign or proportionality sign, you now have what we call resistivity, L over A. So we can say that the practical or experimental formula for resistance is actually this. If anybody wants to really put you to test, is this one that person wants you to use. He will be giving you questions that involves this one, not this one. Very important. So this thing you see here is resistivity. And please, it's not important to me for you to note that practically, from that practical aspect, you don't need to see it that resistance depends on length. It depends on length. It also depends on area. So you see it now. If you have shorter wire, resistance will be what? Low. If you have longer wire, resistance will be high. So it depends on this. But you see this resistivity. Shabi said introduce the equality sign. Once I introduce the equality sign, anything that comes as a constant here is constant. It does not depend on anything. So resistivity does not depend on resistance. It does not depend on length of the wire. It does not depend on area of the wire. Note it somewhere that I said it.
It does not depend.
Resistivity. Anytime you introduce equality sign, that constant there does not depend on anything around it there. So resistivity does not depend on any of these things. Rather, resistivity just depends on the type of material or kind of material. It only depends on the type. This resistivity depends. Shall you see why I wrote it? It's different from this thing. This one is for density, rho. This one is resistivity. So I said, resistivity only depends on the type or kind. See it this way. If the man is short or the man is tall, and you like tall or short, that is talking about resistance. You are resisting. But when it has to do with resistivity, he's checking what type or kind of person that thing is. That is resistivity for you. So if that thing is a metal or an insulator, that is resistivity for you. Can it conduct electricity easily or does it not conduct electricity? So this is what resistivity is talking about. So if I know that something conducts electricity, that means that the resistivity is low. While if something does not conduct electricity, that means that the resistivity is high. So very important. So we said that poor conductors equals high resistivity. While good conductors equals low resistivity. It's in tutorial class that impregnate you academically. Once you are able to follow me, we do everything about this chapter 4, step by step. You did not miss any class. If you like, don't come for magnetism, but stay calm. But you have conquered a lot. But please, come for all your classes. But what I'm saying is that this chapter 4 is the reason why we started from chapter 1. Chapter 4 is the reason why we have to do chapter 1, chapter 2, chapter 3, chapter 4. So that when we get here, there will be no issue. Because this is where everything is. Because assuming I started chapter 4 without teaching you quantization and I come and be doing it now, everything will look strange. I want to clean. Can I clean?
Yes.
So see, the same way I'm teaching you everything on Ohm's law, DC principle 1. That's the same way I will teach you principle 2 and principle 3. Principle 2 and principle 3 involves us drawing a lot of circuits. Understanding what is loop. The inside of every circuit that is big, the inside, the space there is a loop. Just like if I come and say that everything you are sitting down now, this section you are sitting down is a loop. Sitting down is a loop. This side is a loop. So everything here is a loop. So that is what I. So from principle 2, principle 3, we will be doing more of circuits, diagrams, interpreting diagrams. It's part of the scheme of work. And it's in that principle 2, before I start it, I'll first teach you resistors in series and parallel. Alright, now please, V is equals to IR according to Ohm's law. Now let's compare the relationship between Ohm's law and electric field. Do you remember that V is equals to ER? Is it not true? Shade? Electric field now. This is electric field, this is R. So, but notice something. The R here is not resistance, sure you know. It's talking about distance. So since it's wire we are talking about, we replace this with what? L. I started with that so you remember. That's our earlier. So please equate these two. So that you now have EL equals to IR. If you equate EL to IR, you will now see that making E subject of the formula, but before we do that, EL equals to I. Oh yeah, give me. What is the value of R? Using that our resistance, practically what it depends on, that is resistance. Hey, Jesus. Now you go. Which is the same thing as saying I resistivity L over H. This will cancel this. Now notice something. E will now be equals to I over A and resistivity. Now, did you remember we once came across I over A?
Yes.
Current over area is what?
Density.
Is it charge or current?
Current density.
Please, I know your textbook called it charge density. This is called current density. Don't mistake it. Current density. So J for current density and then resistivity. So please note it. Relationship between voltage, the relationship between Ohm's law and electric field simply gives you that electric field is equals to current density times resistivity. Have it in mind. And do you know that this thing you are seeing here, also means something again. Something again. If something is not having too much resistivity, if a material, I told you that a material, resistivity talks about type of material or kind of material. Another thing that talks about type of material or opposite of resistivity is simply conductivity. So if the material is conductor, the conductivity will be high. If it's a non-conductor, the conductivity will be low. So for that reason, this resistivity that I see here, this thing like this, is equals to 1 over conductivity. It's the same thing with this for slipping. That means that conductivity is equals to 1 over resistivity. So conductivity is in tutorial class they impregnate you academically. I hope you are learning. If you like, as I'm teaching you, you'll be somewhere sleeping. After you read it in your textbook, be playing. Just be playing.
I said that conductivity is.
I said conductivity is the opposite of resistivity. This thing is 1. 1 over, not I, 1 over. That is why I started putting this thing so you don't mistake the two. I say it's the opposite of resistivity. That the high, if it's a good conductor, conductivity will be high. If it's an insulator or a poor conductor, conductivity will be low. So if I know that, I'm not saying that this thing that I have here, this electric field, can also be written as E equals to J1 over what's it called? Conductivity. What am I doing? So 1 over this, which is the same thing as saying that E is equals to J over conductivity. So electric field, relationship between Ohm's law and electric field. Electric field is the same thing as current density, product of current density and resistivity, and is also the same thing as division of current density by conductivity. So note that. So note this thing. Note this thing. Note these things. And please, if that be the case, I want to still do something. Can I claim? Do you remember that we once said that R is equals to resistivity N over A? Is it true? Yes. Which means that if resistivity is 1 over conductivity, resistance can also be defined as saying 1 over conductivity N over A. Is it not true? Which means that resistance is also defined as saying N over conductivity A. Note it. Put it somewhere in your notebook. Once you know all these things, you don't have any question to ask in the exam hall again. Once it concerns resistance, Ohm's law, the first principles to here, you can note all these things now. No question at all. The next one I'm going to teach you is power, electrical energy. Once we are done with that, we'll start solving questions. Now, so that by next class, I will now start with second principle and third principle. We must cover them. We must cover. Copy, be fast. Be fast. So please, watch, see. I want to clean this thing. We are still in the first principle. Now, what this thing means also, see, this is resistance. Do you know that if I want to make resistance such a formula here, I can say that this is the same thing as saying RA over this thing L, divide by L. Do you know that resistivity is equal to resistance times area all over length? Note all these formulas for me. It's the same thing about you need to rotate it, because if you don't rotate it, you might not be able to think when questions are given. So, for conductivity, just from here now, this one is from here. So from here now, that I have R equals to L over conductivity times A. If you make such a formula, this will be the same as saying RA conductivity. Somebody said God. God is in heaven.
So this last one you don't understand. Because R over L.
Well, see. Let's do it together. This thing is. You agree it's the same thing? If this come here, it's RA and Sherry.
Okay, you cross multiply.
So now that I have this, making the conductivity circuit formula, you now have LO over RA. So please note this as well. So conductivity is also this. You can also do 1 over everything here, which is going to give you this thing. So resistivity is also this. From. So note that. So please, with that said, write for me subheading. Let's be fast. Let's be fast so that we solve questions, because you are taking time for me. You will tell me when I started this class.
By 2.
Somebody said it doesn't matter. But that's what you said now. To you, it doesn't matter to you. But it matters for our academic growth. You don't know. How can you be here without knowledge?
Okay.
Your head is full. How can your head be full? You don't know that the way God created the head is that if it's full like this, provided there's food in your stomach, you can just eat. But you did not eat before coming. So they always tell you to eat before coming. Well, see, let's be calm. We'll get there definitely. Let's just be fast. Just be fast. Let's be fast. I want to finish. Just write for me. Electrical energy and power. Don't worry, we'll soon dismiss. Electrical energy and power. Electrical energy and power efficiency. Electrical energy, power, and efficiency. Electrical energy, power, and efficiency. Okay, so see, when you hear energy, you know already that energy is the ability to do work. Is it not true? Do you remember that we once said that voltage is equal to work done in moving a unit charge? Do you still remember this thing? So if I know this, we'll then come and say power itself, power itself is equal to work done. Rate of work done, is it not true? Sure, you still remember? Now let's make work, because anytime I'm talking about energy, I'm using work, they are the same thing. So work now will be equals to VQ. I've derived this, done integral part of it when we did energy. Those of you that missed our last class, go and check our video how to derive this using integral and the rest. We've done it. That's not what I'm going to do here. My own is to solve today. So now that I have this, what about Q? Since we're talking about electricity, from I equals to Q over T equals to IT. Is it not true? Sure you know. Charge will simply be current times T. So if I know this, I can also say that this energy here is the same thing as saying W equals to VIT. Sure you agree? Carry it and come here now. P equals to VIT over T. This will cancel this. P equals to VI, or say IV, the popular one. So power is known generally with this, but this is not where we stop. We now need to come to Ohm's law, comparing this. So comparing energy to work. Comparing this energy to work, we get this. I want you to always think of it from this angle. If you can notice it as subheading, it will help you. Comparing energy and work and power, you get this. Now, comparing voltage to power. Remember, voltage, according to Ohm's law, comparing power to Ohm's law, sorry. So this one is energy to voltage. Sorry, this is energy to voltage. Comparing energy to voltage. So we got from there to this point. Then we know that charge is. Then now I'm comparing voltage. Can I say power to Ohm's law? What am I doing? Comparing power Ohm's law this time around. Naturally, the main part, I don't want to talk about it because I can't talk about power and work without talking about work. So there's no need saying I'm comparing. So this is now going to be P equals to I. Now V, according to Ohm's law, is what? IR. So P is going to equal to I times I. I
still
square.
deriving the
Be playing. Just be playing. Oyinkebu Onaya. Serious student. If you say stay here till next year, there will be 3 points in billions. People can stay here till next year. Someone said because of the money. You don't know that what you're learning now is much more than the money. It's not much more than the money. Okay. Be playing. You don't have your exam. Don't write it. Get the permit again. Okay, I thought it's biochemistry. You're supposed to do biochemistry. There are people that say the kind of thing you just said. All those biochemistry, physics, maths, all those departments, the seniors will tell them, if they're going year 1, 200 level, they will arrange it. But medicine, somebody, all those medical students should know, need that, you can have a back lane, now right here, I will pay you. Oh yeah, please, let's be fast. Please, do you remember that I is equal to Q over T? But please, I know you want to go on, but please, endure. Let's substitute. What am I doing? If I substitute this, I think I'm going to get back my... Okay, I is also equals to V over R. Am I correct? So let's try the two. Let's check the two. So I have Q over T all squared R. So P equals to Q squared R over T. You think it's not valid? T squared. You think it's not valid, but it's valid. Now let's check when we compare this inside here. I'm carrying this. I carry this inside here. So let's say I carry this one inside here as well. So I have P equals to V over R all squared, then R. Then I'm going to be having P equals to V squared over R squared R. This will cancel this. P equals to V squared over R. Sure, you know that the truth is that if I want to derive a lot of things from this power, there are many things I can derive from this. Do you remember that V is equals to ER? Sure, you remember? Is it not true? At that point here I had, what am I doing? Yes, at the point here I have this. At the point here I have, which one? This. Let's check here now. Let's check what we have here. Since I have this square inside this, I can have P equals to ER all square over R, which is going to give me E square R square over R. This will cancel this, so that I have E square R. If you like, think it's not valid. All these things are valid. It depends on what you are given. So once I should come down, Shabi, you are rushing me. You are the one rushing me. You go home. If it's time, you go home. Then please, the next thing I want to show you, I want to clean this. If they ask you the cost of electricity, I want you to know that any question that asks you cost of electricity, for example, the current you use in your house, power holding EEDC charge you by energy, not by power. So if you know that, it simply means that anytime you hear cost, it's going to be simply energy times per kilowatt hour. That is energy times amount per kilowatt hour. Cost, if you hear cost, any person that asks you what is the cost, is simply going to be energy per kilowatt hour, or you can convert the kilowatt hour. So energy times amount per kilowatt hour. This is essentially I say you can say watt seconds as well if you convert. So note this. Now for efficiency, they can ask you, they can tell you that something happened at a particular percentage, that energy was used at a particular percentage. Energy was used, and then the efficiency of the energy that was used, the sourcing something, maybe 80%, 50%, or whatever percent. They are not telling you to find how much was used. So in that case, the how much used, we normally represent it this way, is going to be simply equals to the decimal. The decimal, that is the percentage used in decimal. And we know that if I have something like 80%, it's setting as 80 over 100, is it not true? Yeah. So which is in decimal is going to be 0.8. I'm going to give you the formula, or just note it. So the decimal of whatever percentage you have decimal of the percentage given times the energy output. So in formula is given this way, N equals to, you see, inputs over output, or you say useful work. So we normally say useful work over output. So this N here talks about that percentage you are giving. So this is going to be the percentage. Okay, this is supposed to be my percentage. What am I doing here? I'm putting inputs as this. Don't worry.
You are hungry.
You see there is hungry. You see there is hungry. I'm checking something. Sorry. Don't worry, I know what I'm doing. Wait. It's supposed to be what entered inside first and denominator over what came outside as the output. So this is supposed to be output. As we start solving question, we will still do it. It's just that you are rushing it. So times inputs, you don't. So it's supposed to be outputs. What am I doing here? Energy. Don't worry, just write for me, please. So whenever you hear cost, this is your formula. Whenever you hear efficiency given, this is the formula we are using. So as we start solving questions, it will be possible. So please check the first question here. Let's just do one question and we go home. Just check that our group. Check our group.
So this time you are
just solve one question, we go. There are so many things we can derive from that power formula. Like just that, let's stop there, but as we start solving questions, if we have any need, we still go back. There must be need. We will touch past questions. So all the questions there, we just solved one today. Our class on Tuesday, we now try to solve everything. Don't follow your footsteps, so. Don't follow their footsteps. There's somewhere to be.
like this time.
I see. That one that has 8 pages. That one that has 8 pages, check any question there. For that one that has 8 pages, let's solve any question there. Then go from Tuesday, we'll now try to solve all the questions I've posted here because it's 2. One is 3 pages, one is 8 pages. For that 8 pages, so let's just solve one question here. So check which one are we solving there. Oh yeah, give me number 1. Let's start with the first one. Let's follow it one. Number. What's the number 4? Right. Let's. You know there's one that has 8 pages, one with 3 pages. Then there's one that I gave notes. So we are going to solve all the questions because all the questions there involves everything that is just on the first principle. So that when we get to the second principle, by the time we do second principle and third principle, we'll do it together. Then we'll go to the textbook, back of textbook, our exercises and solve everything there. So just give me any question there from this one. Let's do just one of it. Then Tuesday we'll continue. Oh yeah, read. Question what? Somebody said 4, eh? Read. Don't worry, we'll touch everything. But it's just maybe because this one said first. They pointed this one first. Read. Read it, let me hear. Inside the WhatsApp group, check the WhatsApp group. SLE.
Resistivity of 0.5 ohm meter and a charge carrier mobility of 0.02
and charge carrier mobility
of 0.02 meters
of
0.02 meter squared per
Yes. Okay, now I see why you people chose this one. Okay. Okay.
Velocity of the charge carriers.
What is the drift
velocity of the charge carriers?
Okay.
When the voltage of 10 volts is applied across a 1 meter length.
When the voltage of
10 volts is applied across a 1 meter length.
across a 1 meter length. Please let me read it so you check if what I have is what you have. A semiconductor has resistivity 0.5 ohm meter. That's the unit of resistivity. While that of conductivity is ohm per meter. And charge carrier mobility of 0.02. That's what you gave me. Meter square volt second. Check for me. Is it VS you have there?
Meter square per volt second.
Per volt seconds. Okay. Thank you. Full stop. What is the drift velocity?
Of the charge carriers.
Okay, of the charge carriers. Okay,
When the voltage of 10 volts is applied across a 1 meter length.
Okay, thank you. God bless. So now let's write solution. I've told you before, there are some things you don't know the answer. Once you write solution, inspiration will come. So, solution. You try it small like this, small, you are thinking, you can align. Inspiration will be there. Alright, so let me pull out resistivity. Every material on earth has resistivity. In the sense that if that thing is a conductor, we have low resistivity, but a particular conductor's resistivity, the type of conductor, will be different from this type of conductor. If steel, copper conducts, its resistivity will be different from, steel stone will be different from copper stone. So charge carrier mobility. Shall you remember this thing now? Because it's 0.02. Assuming we even know what it means from the beginning. Now they then gave us voltage V equals to 10 volts. Now they gave us length equals to 1 meter. The importance, like the most important thing I tell students in this course is everything given, every single thing mentioned will be very important. Just like if you were in our last class, I told you that anywhere you see full stop, it means something. If you hear something was connected before now being connected to another thing, don't say, okay, it was broken. Let me just know. Every connection did something. If possible, if you don't know what they're asking you to find, calculate everything. Find, if you hear something was connected before being broken and connected, calculate everything for that connection first. Use everything you have to calculate charge. If it's capacitance, resistance, should be anything before moving to the new connection. So now that we have this, let's now check. Drift velocity is what I'm finding. Vv is equals to mu E. Is also equals to Vv is also equals to L over T. Is also equals to
I over.
NEA. Shemi?
Yes.
But see now, child of God, these three things that I know, it's good that I know the three. But the thing I will now use to check, do I have current here? Somebody might say you can find current, you can do this one, no problem. But I will have to stress myself if I can get everything I need before looking for that. I can say that from V equals to ER. E, but when it's Y, it's no longer R, it's now L. E is equals to V over L, Shemi? So voltage given is 10. Length is what? So E is what? 10. Shall you see? So, and they gave me electron mobility. Is it not true? And I've gotten E. So I can just find this V here for myself. Now when I find this, that means I will now do 0.02 times E, which is 10. So drift velocity will now be equals to what? Is this 0? Is this 0.2? 0.2. Be sure, which is a meter per second. Now please, this is my drift velocity. If somebody now wants to say, well, what about length over time? They did not give me time here. Then, what about current using V equals to IR? I can actually do that, but that's a longer process. So the answer is simply this. I can actually say, if I do, that is V equals to I, resistivity, L over A for resistance here. But still, I don't have current. Still, I don't have current. If we check all the measures. So this is the one that I'm supposed to use. So this is my final answer. So please, it's important to me that you note all these things. When it has to do with current, when it has to do with electron mobility and electric field, when it has to do with just length and time itself. So with that said, I know this is the junction where we all like the most. Somebody should pray for us. Let us go. We've tried. Why I say we tried is that we're able to cover the first principle. That was my goal today, to see that we cover first principle. So in our next class on Tuesday, our class on Tuesday will be more of maths and physics. That class will be on solving the questions. So that by winning that next week, I must make sure we do. Winning next week, I must make sure we enter second principle, which is Kirchhoff's rule, KCL and KVL. Then by next week Saturday, by coming Saturday, we should do what's it called? The principles and the textbook exercises. So that upper week we now enter chapter 5, which is magnetism. Oh yeah, pray, let us go. Pray, oh. Who is praying for us? Amen. 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 May the grace surely okay, please go home straight, don't branch, be safe, be careful, don't press phone on the road. If you've not paid us for tutorials, let it not pass Tuesday. Try and pay us.
I want my receipt.
Okay, I've not given you receipt. Tuesday, you meet me early in the morning. Please, if I'm owing you receipt, meet me early enough. Please, it's not compulsory to pay ICT. Can't pay anything 1,000. It's by choice. It's by choice. Please. Because I know some students, the way it is, some students think it's compulsory. And they've been asking. It's not compulsory. Some persons are being paid thinking it's compulsory. Some persons have told their parents. So it's not compulsory. Ngwan, yes, I tell your mom it's not compulsory.
No, I know. I just wanted to find out.
Okay, Ngwan now.